Okay, hi everyone. My name is Barak Dayan. I did my postdoc in Caltech with the late Professor Jeff Kimball on cavity QED. We were doing the first demonstration of photon-atom interactions on a chip back in 2006. In the last 15 years, I'm the head of the quantum optics group at the Weizmann Institute in Israel. And 4 years ago, I co-founded the quantum computing company Quantum Source, who actually deals with photon atom gates. And I will tell you about it more at the end of the talk. And I was asked to give some inspirational talk about how important fundamental science is. I think I'm preaching to the choir, but let's have it, I guess. I'll try to make it fun as possible. I would like to talk about three discoveries and how they were so pivotal and important in shaping global powers. So let's begin. So the first discovery I would like to talk about dates back to 1862, James Clerk Maxwell. So he's a mathematician, and he was playing with equations of electric and magnetic field, known by Faraday, for example. And he was trying to make them more symmetric, to make the roles of magnetic and electric fields be similar. And doing that, he realized that there probably should be another term here. And he inserted that term into the equations, played with it for a while, and boom, he got a wave equation. And what's interesting about this wave equation are two things. One is that at the place of the equation where you see the velocity, he got a constant of nature, 1 over the square root of the electrical and the magnetical constants. So this is the first time that the speed of a wave was a constant of nature that does not depend on the velocity of the receiver or of the emitter. It was really weird, and what's even more surprising, and I'm not sure how much he was surprised, but it was definitely a revelation, is that when he plugged this number into the non-existent calculator, he found out that this velocity is the speed of light. Yeah, goosebumps, always. So in 1862, now I'm imagining, alone at night, James Clerk Maxwell was the first human being to know what light is. Aristotle didn't know it. Newton didn't know what it is. It's an electromagnetic wave. So a change in an electric field changes a magnetic field, and so on, with no need in any medium. And this is actually very intriguing, because if there's no need in any medium and the velocity is constant, it creates really weird behavior. For example, if you run towards a pulse of light, it propagates towards you at the speed of light, regardless of how fast you're trying to run from it or towards it. And of course, the person to realize that this is not just a fluke or a mathematical issue, but that this is something real was Einstein many years later. And that's the theory of relativity. And theory of relativity, as you all know, the two theories of relativities tell us that space and time are distorted or warped or mixed both by moving at high speeds and by gravity. And at the time, I'm sure, it seemed really far-fetched and not relevant to anything on Earth. However, as we know today, this is something very, very important. So when we navigate, we know that the time of the GPS satellites moves slower because they're fast compared to us, and faster from the other perspective because they're further away from Earth. This is how we all navigate. And of course, it brought forth the most famous equation of all, E equals mc squared, which gave birth to nuclear power, nuclear weapons. So undoubtedly, realizing something fundamental, as weird as it sounds and as far-fetched as it sounds from real life, eventually leads to very, very big consequences. Today we define who's a global power by who controls these principles. Now, so that's one discovery. The second discovery came a little bit later, and it actually started from exploring how things emit light. So today we call that black body radiation. You heat some iron and it starts glowing. And nobody could explain accurately enough how the curve of black body radiation looks like. And until Max Planck came in 1900, and he hypothesized, for him it was just a mathematical trick, that energy does not come in continuous quantities, but in discrete quantities, like in coins. And in order to make the black body radiation fit what was observed, he had to assume that the coin, the unit of energy, has a value that's proportional to the frequency. Today we call that factor Planck's constant. I'm sure he didn't know that it's going to be called Planck's constant. And this is another goosebump event, because thinking, discovering a constant of nature. This is the constant of nature that tells us if quantum mechanics is real. If H was 0, there were no quantum mechanics. So, if you're religious, then who made H, right? It's God. So it's something that is part of the fabric of the universe, really amazing. And as I said, for him, it was considered rather a mathematical trick. And again, the person to put the principle behind the idea was, again, Albert Einstein, who said it looks like particles. Even light, its energy comes in discrete units. It looks like particles. That gave birth to the concept of the photon. And later on, together with many others, Niels Bohr and Wolfgang Pauli and of course Erwin Schrödinger, they formulated into what we know today as quantum mechanics. Why quantum? Because the units of energy are discrete. So if you have to explain in 2 sentences what is quantum mechanics, so first of all, everything in the universe is described by a wave. A wave can be positive, a wave can be negative, two waves could cancel each other, a wave must answer the Fourier transform, which they called uncertainty principle, because they weren't engineers, they were physicists. And it's a wave, so even if you calculate the fall of a basketball, you can do it by, you plug into H, into the Hamiltonian gravity, and you get a bouncing ball. You solve the wave equation. Not always you know that. However, so what's the difference between regular waves that we knew so far and quantum mechanics is the fact that the waves can be occupied with single particles, with single units of energy. So the energy in each wave comes in discrete quanta. So there's no wave-particle duality. Anyone who says the electron, no kidding. Really?
It's a quantum world.
No. Really?
Yeah.
How can that be? Yeah, but I started like 5 minutes late. Okay. So, so everything in nature is, time is warped when you're having fun. So quantum mechanics is the best description of the universe that we have today. And to illustrate that, here's an aluminum ion clock in my friend from NIST, Chin-Wayne Chow, James. And you see he's increasing the height of the table, and you see the time moves faster. You see that arrow at the top. So yeah, so everything today is quantum mechanics. So navigation, we know we have atomic clocks thanks to quantum mechanics. Medical imaging, computers, the distance between the electrodes in TSMC's latest devices is 20 atoms. So of course they wouldn't work if we didn't know that the electron is just a unit of energy in a wave and not a particle. So in some sense, the AI revolution is a spin-off of quantum mechanics. So I think that by now I have convinced you that discoveries are important. So let's talk about the third one, which was actually validated only in 1981. And it's the last time that our view of the universe was fundamentally changed. So the problem with quantum mechanics is that since it is a wave equation, it involves uncertainty, Fourier transform. And the person who didn't like it was Einstein, as always. And together with two other Jewish scientists in 1935, they thought they found the proof that quantum mechanics is wrong. They said, well, your quantum mechanics, not ours, your quantum mechanics says that there's uncertainty. But however, your quantum mechanics formalism allows two systems to be uncertain, but the same. How can that be possible? It's like having two random coins, which always end up one heads and one tails, and Einstein called it spooky action at a distance. So for 30 years, it was considered a philosophical problem and beyond the reach of science until came John Stuart Bell, and he wanted to prove Einstein correct. He proved him wrong. He found a very simple equation that is validated by this prediction. And 20 years later came Helena Span, Philippe Granger, and then a Nobel that proved that it's actually true. Two things can be random, but the same or the opposite. Absolute correlations. So this is entanglement. And it suggests or it tells us that the universe is not local. So you could have these, yes, you prepared those coins in the same place, but still, you could have one coin completely random in the United States, one coin completely random in Israel, and yet they fall always one heads and one tails. Is it useful? Of course. For example, for quantum key distribution. You could send uncertain bits to two parties, but they are known, they will be the same bits. And this was even shown by the very nice demonstration of the Chinese satellites and the latest papers by Zhang Weipa. Even more, it redefines what we know about information. So think about that every morning. Think about every morning I'm giving you a coin, an entangled state of two coins, in which one is heads and one is tails. I gave you no information because it's always the same thing. Whereas if I split the coins and gave you only one, you would get information. And one person would go to the beach, the other person would go to work. So it redefines what we know about information. And so how come half a page have more information than a full page? That's really weird. So this is why quantum computers work. They redefine what information is. Now, are we there yet? So the nice example of the Willow chip, which had 100 qubits, can't break anything because we need millions of qubits. That's not enough. You need the computers to be fault tolerant. So why? Because you have to define a logical qubit that protects from all three kinds of errors. So eventually we need millions of qubits. There's no escape from that. And so in that sense, we're not as good as we were 80 years ago when a mechanical computer saved the entire free world, right? The Enigma. So everybody wants Moore's law to suddenly kick in, and suddenly we have millions of qubits. However, all the material systems, all the systems we have today are still stuck around the hundreds after 3 decades. The first two-ion qubit gate was in 1995 by Dave Wineland. So to have something like Moore's law kick in, we need a system that is modular and where we can do cut and paste. And this is what a photonic computer does. And that's the last few slides. That's a couple of slides. This is what a photonic computer does. It separates the problem. The source is called RSG. It generates small clusters. These small clusters could be duplicated in the cut and paste method in time by sending them into a fiber, which you can't do with material qubits. And of course, you can add many sources together to do a cut and paste in space as well. The problem is that generating these clusters is very hard, turns out to be. This is why PsiQuantum is building half a city to make it. So which was remarkable, and I'm sure they'll succeed, but still, it's something very, very big. So this challenge is the hardest part of a photonic quantum computer, and this is what quantum source eventually does, is generating a deterministic resource, which uses a single atom on a chip. It's hard, but at least it's deterministic, and it's not efficiency of 1 in a million, like in the regular approach, but deterministic. We're launching it next year. This is the company, and thank you.